Good morning, everyone, and thank you very much for giving this opportunity to share some of the work that we have been doing. I'm going to be presenting on behalf of Dr. Sullivan and myself. We have this project together. Dr. Sullivan is not able to join today, but I'll be covering the progress made in both of these projects. First off, I should point out that there have been restrictions with the university. We were not able to function. I think our efficiency was less than 30% or so. However, I'm also very pleased to report that despite that, our department and university has been very cooperative, and for our projects, the progress has been still what we had expected. So let me show you what we did. Just to start off, the overall objective of our project is twofold. One is selection of varieties that are novel and also adapted to Ontario horticulture sector. And the second goal was to develop technologies for mass production of these varieties so that they can be introduced into commercial sector. Going to very specific objectives, as I said, the first part was to either identify and also develop through breeding program germplasm that's novel and it is adapted to drought and low nutrient environments. The idea was to reduce the intake of water and nutrients and also catering for the environmental needs as well in that process. Simultaneously, the idea was to develop novel techniques to improve the production of plants so that they can be introduced into the market sooner and also improve their performance in the greenhouse as well as in the tissue culture systems, which I'll introduce in a few seconds. The factors that we are optimizing to achieve these goals are, especially in the production side of it, are plant growth regulators, culturing them in large bioreactors and improving their performance in the in vitro propagation systems. At the same time, one of the issue with the industry has been the lack of conservation programs. Sometimes the varieties go on for a few years, 2 to 5 years, and then suddenly there is no demand, but they always come back. And at that time, it becomes very difficult to find the germplasm. And one of the objectives of this project is to make a preservation scheme where varieties are available for very long periods of time. So as and when they are needed, they can be recovered and again reintroduced into the system. So these are some of the specific objectives. Another part of this project has been to test some of the varieties, not only for this program, but also helping the industry to put out their advanced varieties to the public and assess their appeal or mass appeal, so to speak. And this is done through a trial garden project at the University of Guelph. This project is running for almost 10 years, I believe. And Roger Shams has been championing it. This year was particularly challenging, but I was very surprised that the more than 300 visitors showed up every day. It was held over a weekend for 2 days, 6 hours a day for the industry and public. The trial gardens is a site where companies and as well as breeding programs can grow their plants, and then they are available for the public to assess and make recommendations. In addition, there has been a new initiative in collaboration with the Landscape Ontario to establish a pollinator garden for research, and this is in the I think in their site at Milton. Here is a shot of trial garden at the University of Guelph, which was held at the Guelph Turfgrass Institute. This probably, and unfortunately, is the last year that the trial will be held here because the GTI has moved to Arboretum on campus, but we hope that even for 21, we should have space and facilities in place to run the trial garden again. But this is what it looks like. There are number of, or there were number of areas that were dedicated to new and already established ornamentals. And as you can see in this picture here, people still were, even with, well, they were wearing masks, of course, but they were quite excited. And I personally attended the trial garden shows on both of the days. In fact, there is a video that has been made to showcase trial garden efforts. And this is in the final stages of editing. I'll be very happy to share this which when it becomes available in next 3 weeks or so. Here is a shot of the Pollinator Garden at Landscape Ontario. David Turnbull, who's the site manager, in collaboration with Roger Shans, held several sessions during the trial garden showcase there, and had the interviews with public as well as industries. It really looked very beautiful when I visited, and has a number of plants that actually attract pollinators for plants. One of the factors that drives ornamental industry is novelty, as we all know. And I took this slide from COHA. So just thank you for a very wonderful website that you have. It gives very interesting information, and I would really appreciate that it is expanded to include all kinds of diversified information. All that this slide needs to show, or means to show, is that the ornamental sector is the second largest agriculture sector in Canada. It is expected to grow 2.5% every year between 2015 and 2025, as noted on the website. And novelty is going to be one of the key factors to push this forward. Coming back to Dr. Sullivan's breeding program, he has ongoing studies, and then some new species are being incorporated as and when an opportunity arises. So ongoing studies were with the Liatris, Thermopsis, and Baptisia, and new species that have been added are Lobelia, Helenium, and a few more. As you probably know and appreciate, that breeding is a long process. It takes 5 to 7 years before any advanced cultivar reaches a stage where it can be put into trial garden. Generally, less than 1% of the germplasm selected actually reaches a stage where propagation technologies are fully applied and the varieties tested in trial garden systems. So it's a slow process, and that's where we're trying to expedite the growth factor, at least, so that as and when a new variety becomes available or a germplasm to be tested becomes available, we can very quickly propagate and test it for its wide acceptance. So some shots of the species in program: Liatris, Baptisia, Thermopsis. Some of the other ones that have been added based on the recommendation and discussions Dr. Sullivan has had with the industry. Some of them have been simply based on their appeal, and many of the sports that we found, and I'm going to give you some account of those experiments just in a minute. The standard practice to test the germplasm is to test them in the greenhouse settings, and then testing them in the field where inputs are minimal. So absolutely no irrigation in most cases, and in greenhouses, very, very controlled irrigation and nutritional inputs. The whole idea is to identify native species that will grow with minimal inputs, therefore taking advantage of their resilience to environmental factors, and also saving on natural resources. I'm pleased to say that some of the selections that were made with Lupinus and Aquilucia were found to be attractive last year, and we wanted to test them further. So they were put in cold storage, and when they were taken out after vernalization treatment, they have started to flower. This observation was taken on February 17th, and as you can see, that the plants look very healthy and they have entered into blooming phase already. Similar observations were made for Amzonia and Baptisia as well. Plants were reasonably healthy and they bloomed actually. And again, this observation was taken on February 17th. A parallel experiment that's running in the program is to test the ability of these plants to withstand salinity. The reason for doing this experiment is that the plants that are adapted to salinity are drought tolerant as well. And at the same time, they withstand other types of stresses as well. Currently, in our preliminary experiments, we are testing sodium chloride resistance, and we start at 10 millimolar concentration. Raising is up to 60 millimolar. This is the general range that the plants can withstand, but generally between 10 to 30 millimolar is the level of resistance commonly found. In our preliminary experiments, we found that Equilegia and Allium were able to withstand reasonably high levels of sodium chloride. So these are the two species, and this is how they are tested. On a weekly basis, they are fed with solutions that are in high sodium chloride concentrations. So here you can see, for example, Baptisia and Helenium, their levels vary from 60 millimolar to 40 millimolar at the time when they start showing some symptoms of yellowing, not serious one. The plants did not die, but their growth was restricted. Inspired by these experiments, we are planning, as soon as the facilities are open for full activity, we will have a mixture of salt solutions that are commonly found in the soils or in greenhouse solutions as well, and run an experiment to assess the effect of saline conditions on vegetative and reproductive phases with multiple parameters of assessment. A simultaneous project that's running along with the breeding program is selection of spores, if we see any. And sometimes you come across with genotypes or germ labs that have unique features. So for example, in this case, the Helenium has a variegated pattern. And in this case, you can see one leaf, only one leaf in the entire plant has a variegated pattern. And it seems that it did attract some of the students on an initial trial, whether it's going to make sense to propagate or not. Yes, it's attractive, and it must be propagated to have a wider assessment in that sense. So this plant has been isolated. Similarly, we found a spore in peppers, the chili pepper. As you can see here, it's variegated, and it's variegated extensively. And we believe that this may be an interesting ornamental with culinary values. In fact, there is a growing trend in home gardening that people would want to produce some food along with ornamental values. This has been particularly a promising feature during pandemic times. So we think that variegated plants like that have huge potential. There are some unusual plants that were detected. For example, a trailing plant of Dianthus was found within the population. It has been isolated. It has a very distinct flowering morphology as well. And that brings me to the micropropagation part of the project. Again, just to emphasize, part one of this project is to isolate, identify, and breed novelty for ornamental species. And part two is to develop technologies for rapid production and long-term conservation. Those are the two major overall objectives of the project. So I'm going to describe to you what has been accomplished in micropropagation area. Here you just see several different cultures that we have currently in our facility for tissue culture. A range of plant species are being optimized and investigated, and many of them belong to the project with COHA. For those of you who may not be familiar with micropropagation, it is a technology that allows us to produce a large number of plants from cultured cells, tissue, and organs. These plants are regenerated from very small amount of tissues, and therefore it is called a very rapid, high volume, year-round production technology that produces uniform, vigorous, and disease-free plants, which has another advantage that it poses minimal international restrictions for transfer of material. This is what a micropropagation system may look like when optimized. So this is for Baptisia. As you can see, these plants came from 100 milliliters of medium. So just in a small bioreactor, there will be at least 6,000 to 7,000 plants in it. Some of these buds that are small now, if they are separated and grown independently, they have the capacity to develop into complete plants. And we hope that this is this would be the endpoint for every species that we investigate. Again, I make it sound like easier than what it is. It does take a lot of research to optimize these conditions to achieve such level of competence for plant production. However, micropropagation is part of this overall scheme that we run at the Gosling Research Institute for Plant Preservation, which is also a partner for the COHA project. The idea is to establish a program within Ontario where we have a centralized system to conserve important plant species for the ornamental sector. We call this as a CPR model, which means the propagation, conservation, propagation, and redistribution. It's based entirely on micropropagation. We can produce plants in very large numbers. In case they happen to be endangered species, they are meant to go into their natural habitats, and that's a conservation program. It has a relevance to our current project as well. I'll show you that in a minute. And for horticulture industry, as I described, the large scale production system plus the cryobanking. It's a new term that I'm introducing. Cryobanking refers to conservation of conservation of plant species in liquid nitrogen at minus 196 degrees Celsius. And at that temperature, and that low temperature, plant cultures can be maintained over a very long period of time, almost indefinitely. But with technology in place, we can take them out and again propagate to produce very large number of plants for the industry. So that's the overall scheme of the program. The IPPS term introduced here refers to integrated plant production systems, which is the objective of COHA, which includes the identification of varieties and the production systems. So here are a few examples of what we have done over the last year. We have introduced several new plants. Chrysanthemum was not originally part of this project, but we have introduced it in view of the industry recommendations. Chrysanthemum is a huge crop in Ontario, but unfortunately suffers from a number of viral diseases, and which really restricts the import of high quality plants from abroad. Therefore, we have to rely on what's available within Ontario according to industry recommendations. So we have now developed a program where we're going to introduce disease resistance as well as cleaning up plant species with or chrysanthemum varieties with cryotherapy. Cryotherapy is a kind of a side effect of cryopreservation, if I could use the word. When you treat the tissues with liquid nitrogen at minus 196 degrees Celsius, it has the capacity to eliminate viruses and viroids for many plant species. And we hope that it will work with chrysanthemum as well. However, for now, we have happily growing cultures of chrysanthemum in place, and the cryotechnology will be tested as we go along. There are a number of cultures that we have for variants that were identified by within the program of breeding by Roger Shans. We continuously keep them in culture so that we can propagate it and test them further. Here are a few examples of plants that were that we think are going to be quite interesting and important. Fortunately, two of these species of lobelia are also very important for indigenous community. In discussions with the Six Nations, we found that these plants are on their list of important plants. So we did some extensive work. We are now capable of producing these plants in large numbers. In fact, we can induce flowering just when they are within the culture. So that's, as I mean, an interesting observation. We hope that with this method, we can shorten the time that the plant species take for flowering. But for now, these two plants are in culture, and we do have the technology for propagation.
2 minutes left, Dr. Saxena. 2 minutes left, please.
5 minutes? So sure, I'll finish in 2 minutes now, 2 or 3. Thank you very much for a reminder.
You're welcome.
So orchids is another commodity that we have introduced, and we are able to grow a range of orchids within our culture system. Here, if you can see it on your computer screen clearly, these are really highly prolific cultures that produce orchid plants, and they root very well in our small bioreactors. So they are currently being optimized for greenhouse transplant and field production as well. As I mentioned about the variegated varieties, so some of these variegated plants were identified for their attributes or novel attributes. They have also been put into culture. A good example of this would be a variant of Baptisia, which was isolated for unique floral characteristics, and it is now in culture. We actually can induce flowering in vitro as well, just to test its characters. Same thing happened with the dianthus or the trailing dianthus, a variant that was found by Dr. Sullivan. So it is also in culture. Last but not the least is the approach that we want to use ornamental species that have medicinal value as well. And this sector has become very important. There are many plants that have high ornamental value, but can also enhance immunity. So we just published one paper on a plant called holy basil. In the garden situation, it looks pretty good. Our results from the trial suggest that it could be a very decent ornamental while providing immunity against several infections, also enhancing memory. So very important plant if it's commercialized for Ontario horticulture. Last slide. I wanted to give an example of introducing endangered plant species into ornamental horticulture. That way we serve two purposes. A, there is a novel plant in the system, plus we are saving an endangered species as well. Here's an example of ornamental type lupinus, which we recently published, where we can propagate and also cryopreserve it for long term. And I hope that the model will apply to a number of other species, endangered species that have ornamental value. In summary then, despite the COVID restrictions, we were able to achieve most of the objectives that we had, albeit at a slower pace, but we hope to pick up pace when we are allowed to work full function. And with that, I want to acknowledge people who were working in the program, the postdocs and the technicians. And we also thank GRIP that consistently provides venues and new technologies for this project. Thank you very much.